So in the last video, the word spontaneous or thermodynamically favorable came up. So hopefully you were expecting a connection between the standard cell potential and Gibbs free energy. If you weren't, hopefully the title of this video was a good clue that this is exactly where we were going. So the next section, you will get a lot of equations. It will feel like the information is coming really quickly, but a lot of it is just making connections between the cell potential and everything that we have already connected Gibbs free energy to. So it's not new information, it's just adding in a new connection to the electrochemical cells that we're dealing with. So just starting with an equation to connect delta G, so our standard delta G, to the cell potential, it's negative N capital F, which I'm going to give you a value for, times the standard cell potential. So this right away, before we even define the things, in the example that you had, we had a positive cell potential, and I said that the reaction was spontaneous, which we've also started just referring to as thermodynamically favorable. And the reason that those go together is because of the negative sign in this equation. So if my standard cell potential is positive, then delta G is negative, and you end up with a thermodynamically favorable, or as you will still see it referred to in most places, spontaneous reaction, which means, right, just the opposite. If you have a negative cell potential, delta G is positive, and you have a non-favored or a non-spontaneous reaction or setup. So this is exactly how we'll know, really, if the way that we have set things up is that we have a galvanic cell or an electrolytic cell, or just kind of which direction it will run in based on how we've connected everything. So back to this equation, this N value is the number of moles of electrons transferred in the balanced reaction. So the balanced part is really important. If your half reaction had 2 electrons in it, but then you had to multiply that half reaction by 3 in order to get them to cancel out, the N that you're looking for is 6. So you have to make sure that you're looking at the overall reaction when you do this calculation. And then F is Faraday's constant, and it is 96485 coulombs per mole of electrons. So this seems maybe like weird units, but let's actually do a little bit of unit analysis here, right? We have moles of electrons times Faraday's constant, which is coulombs per mole of electron, times the standard cell potential, which is volts. Okay, well, if you remember way back to the very beginning, a volt is a joule per coulomb. So in the end, moles of electrons cancel, coulombs cancel, and we get a delta G in joules, which is the units that we were expecting. So the units work out here. You will get a delta G in joules. Okay, so this is delta G and standard cell potential. Now, we know that there's already a relationship we've set up and used between delta G and the equilibrium constant. So we can use that relationship to look at how we can get an equilibrium constant from a cell potential or vice versa. So the standard cell potential is equal to RT over NF times the natural log of the equilibrium constant. Now, this, because we do so much under standard conditions, there's actually a version of this where at 25 degrees Celsius, we've plugged in temperature, we've plugged in R, which is the gas constant, and we've plugged in Faraday's constant. So the simplified version is that the standard cell potential is equal to 0.05917 volts over N. Right? We still need the number of moles of electrons in the balanced equation times, now this is really important, someone decided that they would rather work with a log base 10. So this is the log of KEQ. There's probably a natural log simplification version out there. And the only difference between that and this one is whatever constant is used to convert between natural log and log base 10. Okay, so we've got cell potential with KEQ, cell potential with delta G, previously delta G with KEQ. So I don't know if this is helpful, but I've got just kind of a little triangle of relationships here that we can set up. So if you have any one of these pieces of information, you can calculate the other two. So our E cell delta G relationship was the first one we did in here, which is the minus NF E cell. The delta G and KEQ we did in a previous chapter. This is the delta G is minus RT ln of KEQ. And then we can combine those to go between the cell potential and the equilibrium constant. And I'm just going to put the simplified version here, 0.05917 over N times the log of the equilibrium constant. All right, so this is all for standard conditions. Non-standard conditions, of course, come up all the time. And if you think about what is happening in your cell, you very quickly move away from standard conditions anytime you actually run an electrochemical cell, right? This E cell represents a potential. And as the reaction runs, that potential is used up. So we have, just like we had a delta G relationship that would let us calculate non-standard conditions, we also have that for cell potential. In this case, it has a name. It is called the Nernst equation. And this is how we get non-standard cell potential. And the format looks exactly like our delta G format. So the non-standard cell potential is equal to the standard cell potential minus RT over NF times the natural log of Q. And Q is the reaction quotient, exactly like it was when we were looking at non-standard delta G. So this is, with every variable explicit, Just like we did before, if you are at 25 degrees C with the temperature plugged in, and then the two things that are constant that don't actually change, we have a Nernst equation that's just a little bit easier to deal with. So non-standard equals standard. And if you like the natural log, it's 0.02569 over n times the natural log of q. If you prefer your log base 10, it's the standard minus 0.05917 over n times the log of q. I have no preference on which one you use, so use whichever one is easier for you. So the example that we're going to look at for non-standard conditions is something called a concentration cell. And the only reason that this electrochemical cell will run is because of non-standard conditions. So what I'm going to give you is the cell notation for this concentration cell that we're going to look at. We're going to have copper solid with copper 2+ aqueous at 0.010 molar at the anode. And at the cathode, copper solid, copper 2+ aqueous, the concentration of 2 molar at the cathode. All right, so copper and copper 2+ on both sides, and because it's non-standard conditions, or to better illustrate that it's non-standard conditions, I have the actual concentrations listed in my cell notation. All right, so at the anode side, I have copper and copper 2+. At the cathode side, I have copper and copper 2+. So if I calculate a standard cell potential, right, when I look this up in the appendix, this reduction potential is 0.34 volts. So my standard cell potential is 0.34 minus 0.34, which is 0, which is really boring, but is what you would expect, because if I set up copper and copper 2+ at 1 molar, copper and copper 2+ at 1 molar, and connect them, there's absolutely no difference between the two sides. There's no reason for it to go in either direction. But now I have concentration differences. So we need non-standard conditions because we're not at 1 molar. And in the Nernst equation, I've now got my standard cell potential. What I will have to figure out is the N value, so number of electrons in the balanced reaction, and the reaction quotient. So let's write out this reaction. And I'm going to do it in some colors. So the anode is oxidation. So let me get this. I'm just going to do it as an oxidation half reaction. So the anode's losing electrons. So at the anode is where I have copper solid turning into copper 2+ plus 2 electrons. Cathode is my reduction. This is where I have copper 2+ gaining 2 electrons to turn into copper solid. Okay, so if I add these together, the electrons cancel out. So that's my first thing. The number of electrons in the balanced reaction is going to be 2. So that's the value I'll put in. And I'm going to write these with the colors, but I'll label everything underneath it. So copper solid in orange plus copper 2+ in blue, turning into copper 2 plus copper solid. All right. So the reduction half reaction, the copper 2 plus is a reactant, and the copper 2 plus in the cathode is the one that is 2 molar. The copper 2 plus in the anode is the one that is 0.01 molar. So the reason that this makes such a difference is because if you take the reaction copper solid plus copper 2 plus, making copper 2 plus copper solid, and you write the expression for the reaction quotient, it's copper 2 plus over copper 2 plus. So you have to be very, very sure that you know which copper 2 plus is in the numerator and which is in the denominator based on which part of the cell it came from. So the copper 2 plus at the anode is in the top. The copper 2 plus from the cathode is in the bottom. And because we have labeled the numbers with these, we can get them in the right place. So it's 0.10 molar, well, no units, 0.10 over 2.0. That is my Q value that I will plug in to my final expression. All right, so we can calculate this. My non-standard cell potential is 0, which is my standard cell potential, minus 0.05917 over 2 times the log of 0.010 over 2. And in the end, you get positive 0.068 volts, which is not very big, but it's a positive value, which would give us a negative delta G, which means it's thermodynamically favorable, or as some people would say, it's a spontaneous reaction. So this reaction will run until the potential gets down to 0, which is probably going to happen when the concentrations are equal.